Okay. I wish to consider an additional problem before we finish this chapter. Here is an example how we might calculate the electric field, the electric potential of a continuous object. This time we actually have to do an integration. So far, the integration that we did for this chapter really not that much of an integral to do. This one is a little bit more involved, even though it's not that complicated. Okay, you have a uniformly charged rod, okay, of length A. I have an x-axis sticking that way. One end rod is x equal to 0, the other one is x equals a, so the length of the rod is a, and the linear charge density is lambda over a. Now, let's look at a point P, a distance b away from one end of the rod. Okay, what I want to know is what is the electric potential at point P, and what is the electric field at point P. Okay, as usual, we're going to calculate V first, then we differentiate, we get P. We get E. Okay, so let's do that. This is a continuous object. So in order to find the electric potential, what do? Well, you know, I would cut it into little pieces, right? So this is x plus dx. This little piece here, what is dp? What is dv? What is the electrostatic potential created by this little piece at point P? Okay, this is what we want to know. Well, obviously, it is equal to dv P produced by this guy is k dq over what? Over that distance, right? Now, between here and there is x, and between here and there is b, so the total distance is x plus b, okay? X plus b. Right? Now, before I can integrate, I must rewrite dq in terms of what? In terms of dx, and you can easily do that. dq, in fact, is lambda times dx, so this is k lambda dx, and then you have x plus b. Okay. With that, we're now ready to integrate. All right, we're ready to integrate, so let's integrate. All right. X goes from here to there, so it goes from 0 to a. All we have to do is to integrate this. It's 1 over x plus b, so what you get is a log function, right? Natural log function, so you get k lambda. Natural log of x plus b, where x goes from 0 to a, okay, from 0 to a. So what is the answer? It's k lambda natural log of x plus b, x substituted with a, so it's a plus b, divided by what? By x plus b when x is 0, so it's just b. Okay? So that is our answer. Now, once we get that, how does one find this is Vp? Okay. How does one find the electric field at point P? The electric field at point P. Well, be careful here. Which you have to differentiate, right? And which variable do you use to differentiate? It looks like there's no variable here, just a and b, right? Well, which one do we use? A is the length of rod, of course, that doesn't change. But B does. B can change. As you move B, the potential is going to be different. Okay? The potential is a function of B. So as you move around, the potential changes because there is an electric field. That's the only reason why potential changes. So, what is E at point P? It is the negative of dV what? D what? dB, okay? Because B is, the variable that tells where that point is. Okay, it's just like x, but we use that x to denote where the, which piece of the rod we're dealing with. So here is B. So then what you have to do then is to do this. Negative, take the constants out, k lambda, d dB of natural log, okay, a plus b over b. And very simply, after some algebra, d of natural log of x is just 1 over x, okay, you know that. And you will find that it is equal to k lambda a divided by b times b plus a. And lambda times a, as you know, is just q. So it's the same result that we obtained before in chapter 23. If you use the corresponding symbols, P being the distance between point P and one end, you just get the same result. We used L for the length A, but you can check that we actually get the same result. Okay, so this is one additional problem. Another example that I want to discuss involves cylindrical symmetry. So what we have here is actually a homework problem from the textbook. It's called the Geiger-Müller counter. This is used in nuclear physics. As far as we're concerned, we can think of the setup as a cylindrical, infinite long cylindrical shell concentric with infinite long cylinder. Okay, the cylinder is charged to a charge density of lambda per unit length. That's the inner cylinder of radius b, and there's outer cylindrical shell of radius a is greater than b, and is charged to negative lambda. Okay, so we can consider in these dimensions both are infinitely long. There is an empty region between the inner cylinder and the outer cylindrical shell. And because you have positive charge here and negative charge there, naturally there will be an electric field, right? There will be an electric field radially outwards pointing this way from here to there. And of course, this is closer to positive charge, so you have a higher potential here and lower potential there. Now, suppose you're given the potential difference. Okay, actually, suppose you're given lambda first. You're given lambda. Can we calculate the electric field in this region, in the empty region between the inner cylinder and the outer shell? And after that, can we find the potential difference? The potential difference between here and there. Well, half the problem's been worked out in the previous chapter because we know how to calculate the electrostatic field of a cylindrical charge distribution. Suppose I want to know the potential, the electric field here at this point, which is a distance r away from the center, from the axis of symmetry. What would I do? Well, as you learned, we would have to draw an appropriate Gaussian cylinder like this, right? Of radius r, and because of the symmetry, the electric flux only goes through the side of the cylinder, and so on and so forth. We go through all this discussion that we had before, and you will find, if you don't check the previous chapter, we did that a number of times. E as a function of r, in between the cylinder and the shell, equals what? K, 2k lambda over r. Okay, we did that before, and that can also be rewritten as lambda over 2 pi epsilon naught r. And that is the magnitude. As far as direction is concerned, it's just radially outwards. That should be a familiar result by now. Alright, given that, can we find the potential difference between the inner cylinder and the outer shell? Well, again, we have to take a certain path, and the easiest path to take to go from initial to final would be a straight line radially away, because along that line, E and ds would have the same direction. Okay, so if the potential here and there, the difference is V, and then that V would be equal to what? E dot ds. Between the inner shell and inner cylinder on the outer shell, and then we can plug that E in. Okay, so it's lambda over 2 pi epsilon naught r dot ds. ds is just dr. Okay, it's just dr. Between this radius and that radius is from b to a. Okay, from b to a. Right? Radius, here's unit vector r dot dr. R and dr in the same direction, so it's just dr. It's just dr. Okay? And then what you get is a natural log function, right? Lambda over 2 pi epsilon naught. 1 over r dr is a natural log function. Natural log of r going from a to b, so it's natural log of a over b. That is the potential difference. Now the nice thing about that is that oftentimes you're not given lambda. Lambda, usually we do not measure directly. Something that is much easier to measure than lambda is V, because all we have to do is hook up to a certain battery pack. So let's say it's 6 volts, for example. Then the potential difference between this point and that point will be just 6 volts. So in other words, V is something we measure directly instead of lambda. But you see, once we know V, we can solve for lambda, right? We can solve for lambda, and then we can plug into here. We will know the electric field at any point. We don't have to know lambda directly, we just have to know V. So what is E equal to in terms of V, not in terms of lambda? Well, what's lambda equal to? Lambda equals 2 pi epsilon naught times V, right, divided by this log function. So I'm going to solve for V from solve for lambda from here is 2 pi epsilon naught times this V divided by the natural log of B over A over B, that is. That's lambda right here. And then divide this thing by what? 2 pi epsilon naught R. Okay, do some cancellation. 2 pi epsilon naught, 2 pi epsilon naught. And what do we get? We get the expression of E as a function of V. Okay, so it's V divided by natural log of B over A, of A over B. Then 1 over R times the unit vector along R direction. So you see, you have a 1 over R electric field as expected. That is anything, you know, outside a linear, cylindrically uniform, cylindrically symmetrical charge distribution. It's always 1 over R. And that is the constant in front of it, which does not have lambda anymore, rather has the potential difference V, which you can easily measure.